Aluminum foil is one of the most deceptively simple products in daily life. Thin, shiny, flexible metal that tears easily and wraps around food, cookware, and countless products. But behind every roll of aluminum foil on a store shelf lies a massive industrial operation powered by molten metal, rolling mills the size of buildings, precision grinders, annealing furnaces, tension-controlled slitters, multi-ton coils, and high-speed packaging lines. What begins as a pool of molten aluminum becomes a sheet so thin it's measured in microns, perfectly smooth, unbelievably strong for its weight, and consistent enough to be used in everything from kitchens to pharmaceutical packaging. And today on the How Factory, we're going inside the giant foil mills where aluminum is melted, cast, rolled, heat-treated, doubled, slit, wound, boxed, and shipped worldwide. What appears simple is actually one of the most demanding metal processing operations on Earth. The process begins with raw aluminum, produced from bauxite ore at smelters using electrolysis. These smelters create enormous slabs called ingots, thick blocks of nearly pure aluminum alloy that arrive at foil mills weighing several tons each. Before any rolling can begin, the ingots must be preheated. Giant furnaces heat them to hundreds of degrees Celsius, softening the aluminum structure so it can deform under rolling pressure without cracking. This preheating process requires extreme consistency. Temperature sensors, thermal cameras, and computerized controls monitor every inch of the ingot to ensure even heating. Uneven temperature means uneven rolling, which can cause thickness variations or surface defects that foil manufacturers absolutely cannot tolerate. Once preheated, the ingot is ready for the hot rolling stage. The ingot enters the massive hot mill where huge rollers, and often more than a meter in diameter, compress it with thousands of tons of force. As the ingot emerges from the rollers, it becomes thinner and longer, transforming from a thick block into a long sheet called a hot band. This hot band is still several millimeters thick, far too thick to become foil, but it's the starting point. As the sheet passes back and forth through the rolling stands, it progressively thins. Sensors measure thickness continuously, feeding data to automated hydraulic adjustment systems that control roller pressure in real time. This closed-loop control ensures that every part of the strip meets precise specifications. After hot rolling, the aluminum is cooled, coiled, and sent to the cold rolling mills, where the real magic of foil production happens. Cold rolling mills use even larger pressures but at ambient temperature. The aluminum strip, now only a few millimeters thick, is fed into a rolling stand with polished steel rolls that squeeze it down to fractions of a millimeter. As the strip thins, tensile forces increase dramatically, so the sheet is held under exact tension. Too much tension and it snaps like paper. Too little and it wrinkles. The rolling mill continuously adjusts speed, tension, roller gap, and lubrication to keep everything perfectly aligned. But aluminum foil requires an even thinner result, often between 6 and 25 microns, thinner than a human hair. Rolling metal this thin in a single pass would damage the sheet, so manufacturers use a technique called double rolling. 2 layers of aluminum strip are stacked together and rolled simultaneously. This allows the mill to push thickness even lower without tearing the metal. Double rolling creates a unique characteristic of foil. One side shiny, one side matte. The shiny side faces the polished rollers. The matte side faces the other sheet. When the 2 layers are later separated, the 2 different surface finishes remain. During cold rolling, precise lubrication is essential. Special rolling oils cool the metal, reduce friction, and prevent microscopic defects. These oils must be meticulously filtered and purified because even the smallest contaminant could scratch the foil. Advanced mills use inline filters, centrifuges, and chemical treatment systems to maintain oil purity. As the aluminum becomes thinner, it becomes more sensitive to microscopic imperfections. Surface scanners, using lasers and cameras, inspect the foil at high speed for pinholes, tears, scratches, or thickness variations. Any deviation triggers automatic adjustments or diverts the foil for reprocessing. Once the foil reaches its target thickness, the two layers are separated on unwinders, creating individual single-layer foil sheets that pass on to annealing furnaces. Annealing softens the foil and stabilizes its crystalline structure, making it more flexible and easier to wrap without cracking. The foil is rolled into giant coils, sometimes containing kilometers of foil, and placed into furnaces that heat them to controlled temperatures for hours. The atmosphere inside the furnace is carefully regulated, often using nitrogen or other inert gases, to prevent oxidation or discoloration. Temperature uniformity ensures the foil softens evenly, so the final product has a consistent feel and does not tear unpredictably. After annealing, the foil coils are transferred to slitting machines. Slitting is where wide coils are sliced into the narrower rolls you see in kitchens and factories. The slitter unwinds the foil sheet and feeds it through rotating circular blades that cut precise widths, 30 centimeters, 45 centimeters, or whatever size the customer requires. These blades must be razor sharp, because dull edges can create rough cuts, burrs, or weak spots. Tension control is again crucial. If the foil is pulled too tightly, it tears. If too loosely, the slit rolls become uneven and difficult to package. Highly automated slitting lines monitor lateral movement, tension, blade pressure, and foil edge alignment to ensure clean cuts across hundreds of meters of foil. As slitting finishes, the machine rewinds the foil into smaller rolls called logs. These logs are then taken to rewind stations, where the foil is wound onto cardboard cores at the exact consumer roll length. 15 meters, 50 meters, 200 meters, depending on the product. During rewinding, embossing can be added. Embossing rollers press textured patterns into the foil to increase strength, improve airflow during cooking, or enhance grip. Not all foils are embossed, but when they are, the process requires precise synchronization between rollers to avoid tearing ultra-thin material. Next comes cutting and trimming. Any rough edges created during slitting are trimmed off to ensure smooth roll edges. The foil rolls then move to packaging lines where every movement is automated to protect the delicate foil. Rolls enter wrapping machines that apply protective film or paper. Printed cardboard cartons are folded by high-speed die-cutting machines and glued into shape. Each foil roll is inserted into a carton by robotic arms or mechanical pushers. Serrated cutters, and the familiar teeth used to tear foil, are added either as cardboard blade inserts or crimped metal strips attached to the carton edge. These cutters must be aligned perfectly so consumers can tear the foil cleanly without shredding. Before sealing, each carton passes through quality control stations. Vision systems check print alignment, barcode accuracy, and box integrity. Weight sensors verify that each roll contains the correct amount of foil. If a roll is too light, it may be missing material. Too heavy, and it may exceed the intended length. Both are rejected. After inspection, cartons are glued or locked shut. Bundling machines then wrap multiple cartons into shrink-wrapped packs for shipping. Palletizing robots stack cases onto pallets with precise geometry, ensuring stability during transport. Pallets are shrink-wrapped to protect foil from dust and moisture, then labeled with tracking data and loaded onto trucks or containers. Behind the scenes, every part of foil manufacturing is guided by advanced process control. Rolling mills use mathematical models to predict how aluminum will behave under pressure. Furnace temperatures are controlled by computer algorithms. Surface scanning cameras inspect foil at tens of thousands of frames per second. Lubrication chemistry is tracked continuously. Even the packaging machines use predictive maintenance sensors to detect bearing wear, vibration changes, or motor strain. The environmental footprint is also carefully managed. Aluminum is one of the most recyclable materials in the world, infinitely recyclable without losing quality. Many foil plants operate with recycled aluminum ingots blended with virgin metal. Rolling oils are recovered, cleaned, and reused. Waste foil is baled and returned to smelters. Heat from annealing furnaces is captured and reused to improve energy efficiency. Water used for cooling is treated and recirculated in closed-loop systems. What makes aluminum foil manufacturing so remarkable is how the process transforms one of the strongest metals into something almost weightless through extreme precision. Rolling metal from inches thick to microns requires perfect balance between force, temperature, lubrication, and tension. Every step, from melting to packaging, demands engineering on a massive scale, but measured in tiny tolerances. The result is a product so common most people never wonder how it's made. Yet its production represents some of the most advanced metalworking technology humanity has ever developed. And that is exactly how aluminum foil is melted, rolled, doubled, annealed, slit, rewound, packaged, and shipped worldwide. A stunning combination of heavy industry, surface science, precision mechanics, and high-speed automation hidden behind a simple, everyday product. Thanks for watching The How Factory, where we reveal how the world really works. Don't forget to like, subscribe, and join us again for more deep dives into the machines and systems behind everyday products.